When you think of Warsaw, Poland, you probably think of the International Mathematics Olympiad, which is certainly the most prestigious high school math competition in the world, and was held in Warsaw twice. The IMO was first held in Warsaw in 1963, and the Soviet Union emerged as the most successful country at the IMO that year. But then, in 1986, it returned to Warsaw, and that year, the Soviet Union and the United States had a draw, tying for the top-ranked country that year. While the IMO is a high school level math competition, that certainly doesn't mean the problems are easy. All it really means is that the problems don't require calculus. And in 1986, the second and most recent year where Warsaw held the IMO, the hardest problem was problem 3. I first read of this problem and its solution, which I'm going to present to you, in Arthur Engel's book, Problem Solving Strategies. Link to buy that book in the description if you're interested. Let's read this IMO problem, then we'll look at a quick example, and then we'll discuss the solution strategy. To each vertex of a pentagon, assign an integer xi so that the sum of the 5 integers, say s, is positive. If x, y, and z are the numbers assigned to 3 successive vertices along the pentagon, and if y is negative, then we'll replace those 3 vertex numbers x, y, and z by x plus y, negative y, and y plus z. So note that negative y here gets turned into a positive because it gets negated. Then this step is going to be repeated as long as there is a y that's less than 0. The question is, does this algorithm always stop? It's always a good idea to try out an example to make sure we understand what's being described here. So let's go ahead and assign an integer to each vertex of a pentagon so that the sum of the 5 integers is positive, and then try carrying out this process. Here's a pentagon with an integer assigned to each of its vertices. Note that there is a negative number, so there will be some stuff for us to do, otherwise we would stop immediately if they were all positive. Now, importantly, the sum of these 5 numbers has to be positive in order for the problem to even apply. So if you add these up, it will be positive. You can check that it's equal to 11. Now the problem tells us in this situation, we should look for 3 consecutive numbers assigned to vertices so that the middle one is negative. In this situation, we can see that would be 4, negative 6, 3. Those are numbers assigned to 3 consecutive vertices where the middle one is negative. So in the language of the problem, we could write this: x, y, z is equal to 4, negative 6, 3. Then we're going to create another pentagon by changing these 3 numbers as the original problem described. So what we're going to do is add y to x, add y to z, and y itself should be negated. So that means in our new pentagon, these numbers are going to be changed as follows. Y gets added to x, okay, so 4 plus negative 6, that's negative 2. Y itself gets negated, and y gets added to z. Negative 6 plus 3 is negative 3. So carrying out that switch, we end up with this new pentagon. See how those 3 vertices are now exactly as we described, negative 2, 6, negative 3. Now, the algorithm is not going to stop because still we have negative vertices. So it is still possible to find 3 consecutive vertices, like 9, negative 2, 6, where the middle one is negative. Now you may wonder, is the sum still positive? We have 2 negative numbers now instead of 1. Is the sum of all 5 of these numbers still positive? Well, if you check the details, actually the sum is never going to change. Because notice, the change we're making is adding 2 copies of y, because y gets added to x and y gets added to z. But then where we did have y, we now have negative y, which is the same as subtracting 2 copies of y. So each time we carry out a step of this algorithm, we're adding 2y and subtracting 2y. So the sum actually doesn't change. You can verify adding these 5 numbers together, it is still 11 in this case. But again, doing as the problem describes, we would take 3 consecutive numbers so that the middle one is negative, so x, y, z in this case would be, say, 9, negative 2, 6. And then again, how we're going to change these numbers is by adding y to x, so 9 plus negative 2 is 7. We're going to negate y, so now it's 2, and we're going to add y to z, so now that's 4. Note, we didn't have to pick these three numbers. In this case, we could have also picked 6, -3, 1, but we picked the three that we picked, and so now after making this change, we get a new pentagon. That gets us here. You can see we now have 7, 2, 4 there as we computed before, and now we would look at 4, -3, and 1. Again, 3 consecutive vertices where the middle one is negative. You're probably getting the hang of the process at this point. We would add -3 to 4, so it would become 1. We would negate -3 to +3, and add -3 to 1, so it would become -2. That would get us to this pentagon, where we would look at 3, -2, 7, so add -2 to 3, making it +1, negate -2, making it +2, and add -2 to 7, making it +5. That gets us here, at which point we would stop, because there is no negative number now, so we can't find 3 consecutive vertices where the middle one has a negative number, so we're done. Of course, we may also note the sum of the numbers is still 11. Now, through trying out that process, of course, we saw that at least one negative number is always turned into a positive, and each time we carry out a step of this algorithm, a negative number becomes positive. It's possible that other numbers switch sign as well, but certainly that one in the middle goes from negative to positive. And we saw in our case the algorithm stopped, so we may think about how we could prove that in general the algorithm stops. The key is to construct a function that we will connect to the algorithm, a function which can be evaluated at the initial step and at every step of the algorithm thereafter. Now, if the algorithm doesn't stop, if it goes on forever, then perhaps this function would have infinitely many values. Now, our algorithm was only dealing with integers, so let's assume that this function also is only going to output integers. We'll construct the function in that way. Now, if the algorithm never stops, the function could have infinitely many values, like we said, but what if the function is decreasing? Well, like we said, we're going to make it so that it only takes on integer values. So if the function were to take on infinitely many integer values and it's decreasing, well then eventually it would have to take on negative integer values. But what if we construct the function so that not only is it decreasing and takes on integer values, but also is non-negative? If we could construct a function like this, which can be evaluated at each stage of the algorithm, well then the algorithm has to stop. It can't go on forever, because if the algorithm could go on forever, then we would have a non-negative sequence of integers, the outputs of this function, that decrease forever. But a non-negative sequence of integers can't decrease forever, because eventually it would have to get down to 0, at which point it can't go on further without becoming negative. Now, it's easy to imagine a million different ways we may take the 5 numbers from a pentagon at each stage of this algorithm and apply some function to it to get some other integer out. And it's also pretty easy to imagine how we might guarantee that it's non-negative. We could, for example, construct the function by adding some absolute values together, or we could do it by adding squares together. Those are 2 obvious choices. The decreasing part is certainly a bit trickier. Now, in the competition, 11 students solved this problem, and one of them did in fact construct a function that was using the absolute values, but every other student found the same function which was using squares. And that function, which is the key to solving this problem, and certainly the hardest part, is this. The function takes as input the 5 numbers on the pentagon, x1 through x5, and the output is a sum of 5 squares. Each term in this sum is of the form xi minus xi plus 2 squared. So then we have this function that can be evaluated at each stage of the algorithm. It certainly is only going to take on integer values because it's a sum of a square of differences of integers. And because it's a sum of squares, we know that this function is going to be non-negative. The squares, of course, are not necessarily positive because 0 is a thing. There are still some details here, though, that are not 100% clear. Note, when I is equal to 4, so this guy would be x4, this guy is x6. What the heck is that? And when I equals 5, this would be x7. What is that? Well, we just have to imagine that we're looping around the pentagon. So if this is x1, bop, bop, skip 2, that's x3. If this is x2, bop, bop, skip 2, that's x4. If this is x3, bop, bop, there's x5. If this is x4, bop, bop, that's x6. So x6 is actually x1 as well. This is x5, bop, bop, skip 2, so x2 is actually x7. So clarifying detail there, x1 we'll say is the same as x6, and x2 we'll say is the same as x7. The other question is, how should the vertices be labeled? It's not obvious at all when looking at a pentagon which number should be x1. Is this x1? Is this x1? How do we decide? Well, we're going to say that they're labeled so that x4 is negative, and of course these are consecutive. So when we look at this pentagon, since this number is negative, we would say that's x4. So then this would be x5, this would be x3, this would be x2, this would be x1. So you've got x1, x2, x3, x4 is negative, and there's x5. So that's our last clarifying detail here. We're labeling the vertices so that x4 is negative, and these guys are consecutive moving along the pentagon. So all that remains for us to solve this problem is to show that this function is decreasing. Again, if this function is decreasing, well, we know that it takes on values of non-negative integers, so it can't decrease forever, which means that the algorithm it's connected to also can't go on forever. If the algorithm went on forever, then from this function, we would have an infinite sequence of non-negative decreasing integers, which isn't possible because there is a least non-negative integer. Of course, that's 0. So such a sequence can't decrease forever. Showing that this function is indeed decreasing as it is consecutively applied to consecutive steps of the algorithm is really just a bunch of messy algebra. It's not particularly difficult, though I will show you the details. Let's first just try applying this to the example that we already went through and see if it decreases. So imagine applying this function to, let's say, this pentagon, which we may consider the second step of the process that we walked through previously, where the first pentagon we began with would be the 0 step. That means this pentagon was the third in our sequence, but it was the second time the algorithm was actually applied. Now, applying this function to see what we get is not too difficult. We just have to take a vertex, subtract the vertex that's 2 steps further, and square it, and then do that for every vertex and add them together. Since this pentagon comes from the second application of the algorithm, we'll call this value of the function f2. And since this vertex has a negative number, that is x4. So this is x5. So 7 here is x1. So we would have 7 minus, 7 minus 4. Square that. So 3 squared. Then we would have x2 minus, negative 3. That's 2 plus 3, which is 5 squared. Then we would continue this process. There's 3 plus 7, 1 minus 2, that's negative 1, so plus negative 1 squared. So the value of our function here would be 9 plus 25 plus 9 plus 100 plus 1. And this is equal to 144. Now, if this is f2, we could apply the function to the next pentagon in the sequence and call that f3. So here's f3. You can work through the details if you want, but once you do all the adding of the squares, it turns out to be 78. So is our function decreasing? Well, certainly in this example, it appears like it might be. We go from 144 to 78, so it appears to be decreasing. But let's actually look at that difference. You'll see that it takes on a pretty interesting value. So f3 minus f2, that's 78 minus 144. This happens to equal negative 66. Now you may immediately recognize that as a multiple of 11, which would come to mind because remember, the sum of these 5 numbers was always 11. The 11 is just a result of this particular example, but the fact that this is a multiple of the sum of those 5 numbers is not a coincidence. In particular, this is equal to 2 multiplied by the sum of the 5 numbers, that is 11, multiplied by x4, specifically from the earlier value of the function, so from f2, not from f3. From f2, our x4, if you remember the pentagon, was negative 3, and this is actually equal to 2 times 11 times negative 3. Now, to show that this function would be decreasing in general, not just in this specific instance, we would want to look at the difference of consecutive terms of the function, just like we did here, f3 minus f2, and we would want that difference to be negative. One way that we could know for sure the difference is negative is if we knew that it was a multiple of some positive numbers times x4, because x4 has to be negative. The other numbers in this product are 2, which is positive, and the sum of the 5 numbers on the pentagon, which, remember from the details of the problem, has to be positive. So indeed, when we go through all the details of the algebra to show this function is decreasing, what we're gonna end up with is 2 times the sum times x4, which we know to be negative because 2 is positive, the sum is positive, and x4 is known to be negative. And of course, showing that the difference between consecutive terms of the function is negative is going to establish that the function is decreasing. Now, in the interest of time, I'm not going to talk through all the details here, but you can stop and admire my penmanship for as long as you need to. These are 2 general terms of the function. So here you're looking at exactly what you would expect for just some term fn. It's just as we defined it, x1 minus x3 squared plus x2 minus x4 squared, and so on. Now, once a step of our algorithm is applied to the pentagon that this function comes from, x3 will be replaced by x3 plus x4. Remember that x4 is taken to be the negative number. Similarly, x4 gets replaced by negative x4, which is why you see x2 plus x4 here, because now the x4 has been negated. Then remember, x3 is replaced by x3 plus 4, and x5 is replaced by x5 plus x4. So when we do x3 minus x5, there are those x4s that were added that get canceled out. And so this looks like it did in the original function. We then, of course, have negative x4 instead of positive x4, and x4 plus x5 instead of just x5. So these are consecutive terms of the function. We then need to subtract them, fn plus 1 minus fn, and see what we get. The details are not particularly pretty, and perhaps I could have formatted this a bit better, but this is what it is. First, I've written fn plus 1 in blue. I've written all of the squared terms first, and then at the end, collected all of the terms that have a coefficient of 2. So this is just expanding all of these squared binomials from fn plus 1. Same deal down here with fn, which is all being subtracted. Now, all of this in orange, fn, is actually going to be canceled out. Some of it's pretty easy to see, like x1 squared minus x1 squared, x2 squared minus x2 squared, and so on. Some of the other stuff you have to look a bit more closely. For example, negative 2x1 x3, that's positive 2x1 x3, which would get canceled out with this negative 2x1 x3. There's a 2 there, negative x1 x3, that's negative 2x1 x3. So there's a bunch of cancellation. In the long run, all of this orange stuff is getting canceled out. Of course, it's canceling out with most of the blue stuff, but at the end of the day, here is what's left. This is what's left from fn plus 1, and we can factor a 2x4 out of every term here. Notice that the x4 squared and the x4 squared would combine to 2x4 squared, so we're factoring a 2 and an x4 out of that as well. That just leaves 2x4 and then x1 plus x2 plus x3 plus x4 plus x5. What's x1 plus x2 plus x3 plus x4 plus x5? It's the sum of all of the numbers on the pentagon. It's what we've been calling S. And we thus see the equality that we mentioned earlier, 2 times S times x4. So we see as long as the algorithm goes on, we can compute new values of this function. This function which takes on non-negative integer values and which is decreasing, because we've seen that if we take one value and subtract the previous one, we get a negative number, so the function is decreasing. But we know because it only takes on non-negative integer integer values, it can't decrease forever, which means the algorithm can't go on forever, which means, yes, the algorithm always stops. So hey, that was a pretty fun problem. Let me know in the comments if you have any questions, and if you enjoyed this video, consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to a bunch of additional videos. Anyways, go Texans!
I'm unstable, I'm feeling hard to keep the cable cut and untuck the cable. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.